Hi, my name's Jake, and I'm presenting my final project today to you regarding my implementation for a 32-bit single precision floating point multiplier. So starting here with my block diagram, we're looking at, initially I pull from ROM two 32-bit operands, A and B, which go into my first combinational logic block where I split up the sign, exponent, and mantissa of both of the operands. So I pretty much have three different paths now: the sign, the exponent, and mantissa, that will follow all the way through to my final answer at the end. So the sign bits, I use a simple XOR block to pull out what the sign, what our final solution sign should be, which is called sign out. And then looking at the exponents A and B, what we do is ripple carry adder to add both exponents A and B from operands A and B, and that will create minuend, which is 9 bits, and that will go into our register block. And then our 24-bit A and B mantissas, what I'm doing to these to multiply the two mantissas is a full adder and AND gate implementation as done in the multiplier from homework 3 part 2. So first thing we do is we add the hidden bit to both mantissas because we need that for our multiplication. And then using the full adders and AND gates, what I do is through each row of full adders and AND blocks, I use all bits A, so bits 0 through 23. And before this first register block, I use bits 0 through 11 on mantissa B. And so the solution to this goes into the register block, and then we go into the second stage of our pipeline. So the second stage for our sign bit, we're just passing the sign bit through each pipeline all the way to the very end, so we don't have to do anything to that. Our exponent, we need to subtract the bias from the solution from the first stage. And so to do that, I've used 7 1 subtractors and 2 0 subtractors to create this exponent win, which we load into the second registry block. Now looking at the mantissa, what I do here is the second half of my full adder multiplier. And out of that comes, I pull out the 48-bit solution from this multiplication, and that goes into our register block. So then coming out of the second register block, our exponent and our mantissa have to be checked to determine if they need to be normalized. And so that's what happens during this stage. We check the exponent to determine if we need to normalize the mantissa and exponent or not. And then following that, I perform the overflow underflow check. And following my overflow underflow check, I update the registers, and that goes into our last register block. And then immediately out of that register block, we have our exponent, mantissa, and sign bits, and I concatenate those to create a 32-bit final answer. All right, I think at this stage it would be great to show you the live demo. So here you can see we're looking at the board, and something noteworthy about my implementation of this multiplier is there's a little bit of confusion whether or not the pipelines were triggered via the clock or via the button input. And so I've decided to leave the pipelining to the clock edge. And so what actually happens is when I press the key, it loads my two operands, and then immediately after 3 clock cycles, that operand has pushed all the way through. And so that's why when I push the button, you'll see the immediate output from the current input. Now, I could have changed this to work with the trigger on the button each pipeline stage, but I decided that this just made it easiest for demoing, although it would be very simple to change from the clock edge trigger to the button trigger, so that we actually have 3 different sets of operands running through the system at any one time. So that's why my demo looks like it does. So starting out, if we look at this, the first multiplication is 10 times 25. The second multiplication is 10 times 45. After that, I multiply 10 times 67.5. Then I multiply 100 times 250. And lastly, I multiply 1005.5 times 300.5. So those are all I'll show for the demo. I have more operands in my MIF file that I created with this. But that is all for my live demo. Let's continue on. Okay, so I'll be brief here, but here's my implementation results. So my 32-bit multiplier used 47 registers, 70 pins, 392 ALMs, and the Fmax. I was a bit confused on which of these was our board, so I included both of them since the frequency is similar in both. So we're close to 162 megahertz with the 85C and about 159 megahertz at 0C. My 16-bit implementation is a little bit faster at 169 megahertz, and this uses 120 ALMs, which is significantly smaller than the 32-bit implementation. Now, to discuss how I optimized this project, I did the optimization to my 32-bit multiplier. And what I did was I changed from splitting the mantissa multiplier in half to doing the first row of full adders in the first pipe, and then all the rest of the full adders and AND gates after that in the next stage. And in doing so, I dropped the number of ALMs by, looks like about 140, and the number of registers also dropped by 8, and my frequency increased by about 20 megahertz. So changing the pipeline split of my mantissa multiplier made a very significant difference in the speed of my 32-bit multiplier. Now, I've attached a slide here where I talk about my additional notes regarding my implementation. So first of all, I've already discussed the point of how I pull in my operands on every key press, but my 3-stage pipeline is actually triggered on the clock. And so if we wanted, I could just switch it to the key to be the same way as we've done pipelining in the past, but for ease of following inputs and outputs, this was my implementation. And I've already discussed the optimization of my 32-bit multiplier. And so my thoughts on the course as a whole, I felt like this class was incredibly intellectually stimulating. It challenged me throughout the whole quarter, probably more than most classes I've taken in grad school, but it was very enjoyable. And the material was presented in a very organized fashion, and I really enjoyed it. And definitely test benches were hard for me to get into in the beginning, but by the end, I learned how extremely useful they are. My only suggestion for the next quarter would be to get out of EDA Playground sooner because it's slow and buggy, and start the students writing test bench code in a better coding environment. So at that concludes my presentation, and thank you for a great quarter. And that is all. Bye.